Welcome to my AI Engineer Roadmap. This video is a compilation of highlights from the full video course, which is available on zazencodes.com. In this video, I'll talk about foundational concepts in AI engineering like programming, math, stats, data science, AI ML, and data engineering. And I'll also talk about AI-specific topics like LLMs, MCP, agents, and other core concepts for AI development. If you learned something from this video, please leave me a like and check out the full course on zazencodes.com, which includes 32 video lessons with a total runtime of over 5 hours. I know that sounds like a lot, but I recorded many more hours than that, and I've tried to condense this into as short as I can. All right, welcome to the first lesson of the course on what AI engineering is. Now, all of the code for this course is open source, and you can find it on GitHub. There's a Jupyter notebook for each section of the course. So I have 9 Jupyter notebooks, and the course itself is on zazencodes.com. So if for some reason you're watching this video on a different platform, you can go there and sign up and start tracking your progress towards completing all of the articles and videos in this course. And the goal of this course is to provide a complete roadmap to all the core skills that you'll need for AI engineering, or that AI engineers are probably expected to understand to varying degrees. And I think we can break down the core skills into 4 pillars, which are clearly distinct. There's programming, just fundamental programming knowledge; data engineering, which very much builds on top of programming and applies that to storing data and doing stuff with data. There's machine learning, which is specific to training models. And there's a lot in this course about doing machine learning and the ideas behind that. And the final pillar is mathematics. Here's how I see these 3 roles breaking down: AI engineer, data scientist, and ML engineer. And I think the best way to look at this data is to look across each row. So for the scope of work, an AI engineer might be interested in something like a product-focused AI application, taking AI and applying it to something. Whereas a data scientist would be less interested in building a product or integrating into a product, but more interested in analyzing data and coming up with some business insights, some sort of report as an output, rather than like a user-facing application like an AI engineer might look to provide. And then the ML engineer is more foundational in the sense that they're the ones actually building the models. So they would be building the models, right, that the AI engineer might pick up and use. That's how I see things. And I'm not saying that this is black and white. This is just like my take on the space. And so now I want to go through what a day in the life of an AI engineer might look like. So in this example, you're this guy who seems to be having some kind of existential crisis. So your product manager comes up and says, hey, there's an issue with the product recommendation system. What am I looking at? I'm seeing a spike in errors. Let me know what you think. And what you might do as the AI engineer is you pull some error logs. So you log into the cloud platform, start digging into the root cause of this issue, find some error logs. Then you might want to replicate the issue in your local development environment, so you understand why it's happening. Then determining the root cause. This is a hugely valuable skill, incredibly beneficial to have for any software engineering discipline. And finally, implementing some solution, obviously trying to fix this problem. Then here's another hypothetical task. Back at your desk, you're excited to work on your task for the day, which is this new RAG generation chatbot. And you're working on creating a conversational agent that helps customers find the right products. And so this is kind of like a classic AI engineer style task where you're doing some prompt engineering, trying to get proper outputs from this RAG system, and you're creating some LLM evaluations in order to determine how effective this RAG system is. We'll talk about both of these in detail when we get to the LLM section of the course. Welcome to the programming section of the course. I'll talk through the fundamental units of what makes up a computer. Cores is pretty straightforward. We can think of each core as being able to execute instructions one at a time. So if you have 4 cores, you can do 4 sets of instructions at a time. But due to concurrency, we can actually switch between tasks really, really, really fast. So even though one core can only do one thing at a time, it'll appear to us like it's doing many different things at once. And for all purposes, it is. But that's due to concurrency. It just keeps switching between those tasks rather than parallelism, which requires multiple CPUs. And we're going to see two types of systems. There's going to be a 64-bit system and a 32-bit system. The 32-bit system was introduced in 1985. And it can only address up to 4 gigabytes of RAM. So older systems we might see are 32-bit, but modern systems are going to be 64-bit, introduced in 1991, and these can do as much RAM as you want. By the way, this information like dates, I include this just for a general idea of historical context. These might not be the completely accurate dates, and of course, feel free to let me know if I'm wrong about these. These are just information I looked up to give us a general vibe of like what's going on. Next, we're talking about bits, bytes, and data units, and this is pretty simple. The bit is a 1 or a 0. This is the smallest unit of data. You could ask Claude Shannon about this, and it is the fundamental like piece of what information is. It's a 1 or a 0, and we can represent like all information aside from quantum information using that like primitive. And now bytes are 8 bits. So byte is 8 of these things, like in a row, like 0, 0, 0, 1, 1, 1, 0, 0, like 8 of these stacked up is a byte. And then bytes are what we use as the base to measure file sizes and so on and so forth. Let me illustrate what I mean by that. Here's a table showing like more familiar files stuff like kilobytes and megabytes. This is how we express obviously file sizes. These are all in terms of bytes, not bits. Every time we go up in order of magnitude, like from kilobytes to megabytes, we multiply by 1024, not by 1,000 like we commonly use with shorthand. It's actually technically 1024. And that's important, obviously, if you're doing big file conversions that need to be accurate. That's how we need to be doing it. Python has a concept of the standard library. And these are like extended functions and classes and stuff that you can import. So they're not available in the default namespace unless you import them. But with whenever you install Python, these come packaged up with it. Here's another couple examples of commonly used standard libraries. There's regular expressions on the left. You can write some regex in this way. And one thing about regular expressions is there's lots of different dialects. So Python has its own like regex dialect that it follows. It's pretty standard, but there's like minor differences with other regex engines. And this is one to note. So there's two path sort of like there's an old way of doing stuff with your paths, and that's from OS. And then there's a new way, which is pathlib. So if you're ever writing stuff where you're doing working with paths, you should use path and pathlib. This is the newer way of doing things with Python, and it allows you to do stuff in a really cool and clean way. Like you can use these slashes. Do you see how we're doing that? And then we can separate data. Like this is how we can define paths using that. It also has all these little cool helpers like .exists or datadir.iterdir. So we're iterating over all the files inside of that directory. Here we're doing something cool. We're listing the files. So using path, we're like, okay, let's look at the data folder and then search for CSVs using this glob. Before, you could have imported glob and sort of called it. But but pathlib is amazing. Use pathlib. Get used to using this. Here's a few external libraries we'll be seeing a lot of in this course. NumPy we don't necessarily always see in a very obvious way, like where we're importing it, but it's used under the hood. It's a requirement for all these things. Like when you install pandas, you're going to need NumPy as well. Same with scikit-learn. And NumPy provides the ways of working with arrays and matrices. Welcome to the lesson on version control. Here we're going to talk all about Git. This is an awesome Git is awesome. Git's super fun. You're going to like this. So it was created by Linus Torvalds. This is the guy who created Linux. And he has this great quote. And I name all my projects after myself. First Linux, now Git. So Linux is similar to Linus. And then Git is it's like a British slang for an unpleasant person. So he's kind of calling himself unpleasant in this quote, which is great. But also this guy's just a legend, right? He created these amazing things. So here's a quick example of working with branches. Let's say we have a branch called feature churn boosted model, and we're working in here. And the idea is like we can make changes in here without affecting the main branch. And then later we can merge it back in. That's what I'm visualizing over here on the right. Now there's a lot of use cases for branching. For example, I use branching in my projects just to like build features and have like a production version and a development version of something. However, a big benefit is with collaborative projects. And when you're doing that, it's important to like follow the naming conventions of your specific project you're on. So I talked about the main branch or master branch. This is like the production ready. That's the idea with that one. And it's usually the thing people see when they go to GitHub. They just see this by default. And from there, we've got feature branches, which could have names like this. This would be like a decent feature branch name, or maybe something like this. So they're pretty descriptive, and they start with feature slash, but this is just a string. There's nothing saying we have to have a slash in here. Just go check out some open source projects, and you'll see tons of different examples of naming conventions, and you'll obviously want to follow the conventions of the project you're working on. The purpose of this lesson is to talk about writing high quality code. So when we're doing this with Python, we can consider the PEP 8 style guide, and this just tells us like how we should do things, and it gives us like a uniform interface for doing stuff. And so there's naming conventions. Classes are camel case. Constants are all caps with this underscore. Functions and variables are snake case, so lowercase and the underscore. That's like how we name things with Python according to PEP 8 style guide. And for doc strings, they should be a max of 72 characters. So that's like vertical. Like if this is our code, we want to make sure that like this is the maximum length that we have doc strings coming, and then 79 characters. This would be the maximum length for the code right here. But this might not necessarily, like this, your screen might have some extra space in here, right? But the idea with Python is that after we get to 79 characters, we should not be writing any more code. And after we get to 72, we shouldn't be writing any more doc strings. Now, I am also a huge fan of type hints for linting. So when you define type hints like this, like get top predictions, and we're saying this has to be a list of floats and this thing has to be a float. Now that means that our linting program automatically knows about this. So as we're writing code, it'll start flagging errors and warnings inside of the IDE before we even write anything, because the system has figured out like what's going on in here. So I think getting used to doing type hinting on the fly is really, really, really important. And now I'm talking about clean code. I've got like a few slides on clean code practices. This is like straight out of my pragmatic programmer book. Like everything, it's a trade-off. So what I'm showing you here, like here, look at this. This is bad. These are bad variable names because I'm trying to read these and I don't understand what these mean, right? But down here, so like hours per day, like HPD is hours per day, and DW is days worked. Like this is so much better down here. This slide is about separation of concerns. So very simply, we've got a function that does a whole bunch of stuff. It's too much. This function is doing too many things. We should split that off. Like let's do the pre-processing of the data, then we'll do the model training, then we'll do the model evaluation, and then I'll run the pipeline in this way. And this is much more readable, especially as our code becomes more complex. But it's another trade-off because we start doing all these functions and it starts creating all this extra boilerplate code. And now we have all these kind of like function doc strings and stuff, whereas this is actually kind of nicer in a way, right? So again, it's a trade-off. And lastly, I've got keep it simple. And this one is really nice for me because it kind of like, it says a lot of stuff that I've been explaining earlier. Like this is complicated. Item for subset in thing for item in subset. If like this is actually fine, but what on earth is this doing? Like it's really hard to figure out. This is much simpler. If I was going to write this, if I was trying to think this through, this is probably how I would think about it in my mind and how I would start writing it. There's no need to take that and be like, okay, let's bunch it down to some optimized Python representation. Like this is just fine. So always try to keep stuff as simple as you can. Welcome to the math section of the course. I really wanted to include math foundations in the AI engineer roadmap because I studied math in school for a few years and I really loved solving mathematics problems and I love the aesthetic of math and writing it and LaTeX. And I wanted to put all of this into the course. We're starting by talking about vector operations. And vectors themselves are just lists of numbers. They could represent various things, like this vector could represent the height, weight, and age of somebody. And this could be a record in a machine learning data set where we want to predict something about a person. And so this becomes a feature, like this is a feature vector. This example below is an embedding vector. This would be an example of an embedding for the word cat. It would be a very simple embedding. It would certainly contain very little semantic relevance. And we'll talk specifically about embeddings with an entire video later in this course. And this is a direction vector, like X, Y, Z, a point in 3D space. So now let's talk about operations on vectors. The first one is a dot product, and this is like a way of effectively multiplying vectors together, but it's done in a very specific way, which is shown down here. So if we have two vectors of the same size, we can take a dot product to output a single scalar number. Here's an example of applying the dot product and its cosine similarity. And this is a common way to get the similarity between two embeddings. And what it does is it measures the cosine of the angle between two vectors. Effectively, what we're interested in is the angle between two vectors, and then we're just transforming that by getting the cosine. And so because we get the cosine, what this does is it gives us a value that ranges from -1 to 1, because taking the cosine of any angle, like even angles above 360 degrees, when you take the cosine of that, you get something from -1 to 1. And the reason for that is, let me draw the cosine for you. So it looks like this. That's cosine, right? So no matter what angle you take on here, like if we could grab an angle over here, this would be just less than like a full diameter on a circle, or we could get something up here, but we're still always going to be constrained between 1 and -1. Okay, so we take the angle between the two vectors. That's this point right here. This is theta. This is the angle on the x, and this is cos on the y. It's cos of theta. So here's an example of a linear transformation from a neural network. And first I'll talk about the architecture of this thing. So we've got a 6-node like layer, and it's feeding forward into a layer with 2 nodes. And so the math to describe that is we have like an input that are six different dimensions, and we want to crush that down into just 2. And this is what we want out. And the way that we're doing that is through this mechanism here, these weights. So we take this one, we sort of squash them with these weights, and we get out something down here. So we'll have 1, 2, 3, and then 4, 5, 6. And for each of these, we want to get 2 things out. So I take that, and I want to go like that and that. And then for this one, I want to send that here and here. And for this one, I want to send that here and here. And then we keep going for the remainder 3. And this is the mathematics, which is expressed by what we're doing up here. And I want to just count these, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what do we have in here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each line here has its own weight. I'm going to repeat that again. And when you're doing this stuff in a neural network and we're drawing lines like this, each line, which represents some sort of like multiplication in this linear transformation, each line has its own weight. It's kind of trippy. Okay, we'll talk more about neural networks later, but I'm going to keep going here. So let's run through this. We need to take the transpose of W so that these align properly. Once we take the transpose of that, they're in the right shape because we have this like six rows here, and then we would have 6 columns in W. And so that would work out. But this T is often like dropped when you're looking at this stuff, or it's like assumed or whatever. But then let's just follow the math through. So we take 1, we multiply that. If we imagine transposing this, now we're going to get, how is that going to look? We're going to switch the 4 and the 2 and the 5. So we're going to have this one is going to be right there. And so that's why we're doing these 2. And then in the transpose version, this 0.2 comes up here. So we do 2 times 0.2, and that's this one right here. And so we just continue taking that through, and we calculate a single number for that first element and a single number for the second. And those are the 2 numbers in the output representation. where the input representation was this, and then the output representation is this, and that's how we get these two numbers here in a neural network feed-forward layer. This lesson is all about probability and statistics, and we'll get to this chart later that illustrates the central limit theorem, or it's part of a series of charts that does that. And here is the most famous distribution. This guy's the GOAT. He's the Gaussian distribution, or the normal distribution. And mathematically, looks like this. And when we plot it, looks like that. And this plot specifically has a couple parameters set. So we have the mean of 0. That's this down here. So it's a mean of 0, and sigma is 1. So the standard deviation is 1, and that ends up giving us this right here, this sort of feature, right? That's how it ends up looking when we set sigma equal to 1. And I want to stress that even though this mathematic looks pretty crazy, the basic form looks like this. So yeah, so this can basically be broken down to here, right? And in that case, I've removed the normalization variable. This is just like this thing out front is just a factor, like a constant factor that transforms this, just pushes through. Nothing crazy going on. In fact, the only parameter is x. And so x is up here, right? So we can kind of just say, well, what if the mean was 0? And in that case, it kind of reduces to just this e equals negative x squared. And so this is fundamentally the same plot as this, just without the fancy stuff. And now this Gaussian, I posit to you that the importance of the normal distribution, the real significance of this, actually comes from something called the central limit theorem. And the central limit theorem to me is one of these little like secrets of the universe. Let me try and explain that to you or convince you of that. Welcome to the final lesson on mathematics. This is calculus and optimization. And we're going to get to this chart about halfway through the lesson when we explain gradients and talk about how to visualize a gradient. Spoiler alert, the gradient is visualized as these things, and notice how they're smaller down here and they get bigger up here. And also notice how they're in a lower dimension than the hyperplane that they are created from. What's going on there? Here's the lesson plan. We'll start with differentiation and get to the gradients, and then I'm going to talk about optimization a whole lot. And we're starting with the basics of calculus. And I like to think about calculus from the perspective of physics and thinking about a real situation where we're modeling the position of an object at some time t. And so if we have that, and x of t does that, we could find the velocity of that thing by taking the derivative with respect to time. How fast is this thing changing with respect to time? That's what velocity is. And acceleration shows us how fast velocity is changing with respect to time. How much is the speed changing actually itself? And so for that one, we take the second derivative of the position with respect to time, or the single derivative of velocity with respect to time. And I believe I worked through that with an example with units. So the units. So we start with meters, and now we're like dividing by, like we're taking d dt, and it effectively divides by time. So in our units, that reflects that. We now see that happening in the denominator. And then we do it again. So now we take the second derivative to get the acceleration, and now our denominator becomes second squared, because again, we're effectively like dividing by time when we do this. Pretty cool, right? Now we've lost some information here. The 3 just disappeared. So when we integrate to try and come back, we can't just retrieve that information again. And that's why when we take the, that's why we add this c. I didn't show that. Okay, cool. So now when we go back, let's say we start with 4 like this. Now we want to get the velocity, and we have to add these constants because we lost some information, and we're like, well, I don't know, the velocity is 4t plus something. I don't really know what that something is. And same with x. And so we get these sort of constant where we're like, well, we know there's, some factor that's linear with time. And we know there's some constant factor, but we don't actually really know like what those things are when we go back. This is more like academic, interesting stuff. Now we'll connect this back to the purpose of this course. Here's an example. So let's do that. Let's walk through this. We're going to optimize a simple linear regression model. We've got this model here, and we've got a mean squared error loss. So this is a real problem, but it's a good toy problem to actually propagate through the math. Let's do it. So we've got some training data. This is our data set. We've got like some feature values, just one single sample, like one piece of data. And we've got some target values, where we want to get to from these features. Now in our training data set, this is what X looks like. And actually what this is in this case, it's a little unclear, but these are 3 different samples. So we have like one of the samples had one had 2, and the other had 3. So 3 different records, 3 different people, if you will. And for each of those people, we're looking for some targets. And we're like, the first one needs to map to 2, and the second one needs to map to 4, and the third one needs to map to 5. That's the situation. So let's start with some initial parameter values, and I'm going to throw these in. So our weight here, this W, it's just a single number, and it's at 1.5. And the bias, just a single number, is at 0.5. So the first step is to calculate the mean squared error loss function. This guy right here. And we defined MSE loss. This is the mathematical representation of this from I = 1 to 3, normalized by a factor of 1/3, and we calculate the gradients of this loss. So we're going to take the derivative of that loss with respect to W, and that gives us this equation here. And we're going to take the derivative of the loss with respect to the bias terms, and that gives us this equation right here. And because we know these, we can now start plugging in values, and we're going to actually calculate an update to these weights. So where we're going with this is we're taking these guys and we're going to calculate the new ones. And we're going to find this 1.5 gets pushed just a little bit down, and the bias gets pushed just a little bit up. And how we get there is we're going to take these loss functions and put them in here. So this dW over dL, that gets used right here. And we're going to evaluate this. Let's work this through. So what I've done here is to plug in this part right here of the equation. I'm calculating first we need to calculate the expected, like the predictions, based on these initial weights and biases. And when we do that, we get this guy right here. And this one was just like running this equation through with these initial parameter values. And so we get this. And now look at this. It's like the predicted value minus the expected value. So that turns out to be, for the first one, and then multiplied by X, right? So Xi is 1. So we're taking 1 and we're plugging that 1 in here. And where does this 0 come from? This 0 is 2 minus 2 from there. Oh my God. Okay, let's do another one. So we have 3.5 and we have 4, and that gives us 0.5. And that's where this negative 0.5 comes from. It's the difference of the predicted and the actual. And then the 2 comes from this feature value 2, which, comes from this X, right? All we're doing is evaluating this X, and this guy here was this term. Whoa, okay, let's get rid of these. And we can like just do this on paper and see this very plainly. And so this 0.33 comes down here. The learning rate is 0.1, boom, 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 and we get our update. And we do the same thing for the bias term. I love seeing real numbers. This is how I understand stuff. Welcome to the machine learning part of the course. We're going to have 4 videos, one on algorithms, data preparation, model training and evaluation, and talking about tools and frameworks. And this video is about algorithms. So in terms of applications, we're going to talk through this chart on the first page. Here's just a couple examples. Healthcare is a huge one, massive benefit to society from healthcare applications of ML. E-commerce has a massive benefit to capitalism and finance as well. Those are just a few examples, but these then represent the 3 kind of different types of machine learning, like the 3 aspects. And we talked about that earlier, but the biggest one, the most important one, is this supervised machine learning. And this is broken down into classification and regression. And we're going to talk through these in this course, in this lesson, these algorithms. And then there's a bunch of unsupervised algorithms, which we'll discuss as well. Here's an example of a regression for doing house prices. To me, this is like the classic regression problem. So let's look at this with scikit-learn. We're going to use linear regression. And so we import linear regression and instantiate it down here. And then after we do that, we fit the model using this line. This is how scikit-learn works. We've seen this before in the course. And here we have some data, and I'm plugging it in. So we're training the data in this way. And under the hood, there's a lot going on when we do fit. And this is generally true with scikit-learn. And we're also going to see later with pipelines how fitting a pipeline overloads many, many different, like more abstraction even than what we're seeing here. But this fit will, go through the optimization of actually finding the parameters such that once we do that, this model object now has all of our parameters contained in it, and we can use it to make predictions in this way. I love the scikit-learn API. It's super nice. Here's an example of training a decision tree with XGBoost, whereas a random forest can take all of the data and just start building all of the trees in parallel right away. XGBoost, the trees that you build depend on the previous trees. So it's an algorithm that builds an ensemble of decision trees sequentially, where each one is correcting the errors of the previous tree. That's the core insight, the sort of fundamental deal with XGBoost. But in terms of applying it, in terms of doing XGBoost, it's very simple. And this is how it looks. So we're not using scikit-learn, actually. We're using XGBoost library. So I'm picking up the library. But this library implements the same API as scikit-learn. So we're using it the same way. We instantiate the model here, and we fit the model, and then we can make predictions based on that fit model. And this fit model here, it's going to be an ensemble. Here's a visualization of the loss curve for gradient boosting algorithm right here as a function of the number of trees. So as we're adding trees, we're seeing how the log loss, the total loss, decreases to the point where we have a really low loss as we get like 100 trees. And if we keep adding trees, our loss should decrease, but we're not making dramatic improvements anymore. And I want to stress that when we do inference with a boosted tree, we're running the input through all of these trees and then calculating the final loss. So we don't just use the 100th tree to do inference. It's an ensemble model where we use all of these trees. This video is all about ML data preparation, and we'll get to this cool looking chart for stratified k-fold cross-validation. For the very first fold, all the purple stuff, this is what we're going to train on, and all the orange stuff, this is what we're going to test on. And all we're doing with stratified k-fold is making sure that we make sure we have an equal representation of both classes in that fold. Because otherwise, with regular k-fold cross-validation, we might find that one fold just has a whole bunch of this, and maybe it has an even split, and maybe the rest of them have no split. So we get bad metrics out of this. Stratified k-fold is the way to go. And you'll also notice, I want to stress that when we look at each vertical chunk, we're only including these once. So the data, we only scan through the data one time. So if we have 5 folds, this chunk here, when we do this chunk here, say for validation, we never reuse that again. In all of the other cases, that specific part of the data is now part of the test set. So that's why this visualization looked so cool to me. I use that as the cover for this slide. And the final type of cross-validation is for time series splits. This one is awesome. So when we're training time series data, let's say this is our whole data set up to the current day. And what we need to do in this case is make sure we're not revealing past data to the model, right? So we say, okay, only train up to this point in time, and then we're going to evaluate on future data. This lesson is about model training and evaluation. And we've already seen a lot about training and evaluation in this course, but we haven't talked about hyperparameter optimization or much about model selection. Here's an example of logistic regression with manual k-fold cross-validation. So when I'm saying manual here, what I mean is I'm actually initializing, I'm instantiating the k-fold cross-validation object like this, and then I'm manually iterating over the folds like this. That's what I mean when I said manual up there, because this is often abstracted into CV. We'll see that. I think we'll see that very soon. And I'm going to talk through the details of this for logistic regression. I'm going to talk through this entire code example, and you need to this thing on the right here. If you're not following this is a decision surface plot. So just very briefly, we have class 1. This is the purple one, And the purple area on the chart is anything the model determines will be a class 1. And then for class 0, the sort of brown area on the chart, or orange, will determine anything that should be class 0. By the way, side note, brown and orange are kind of interesting. There's a video on YouTube. This guy talks about the color brown, and it's actually kind of interesting. Anyway, here's a bunch of examples of different hyperparameters right here for different model types. Let's actually look through these in chunks. So for neural networks, we've got stuff like the learning rate. We talked about this already. We're going to talk about it more. And the number of hidden layers. This is the actual architecture of the neural network in here. For random forests, we've got stuff like number of trees. How many models in the ensemble of how many actual decision trees go into this forest. And also stuff like the max depth, which is like how tall are we allowed to make these trees? How many different, so I love decision trees. They're my favorite type of model. So if we have a decision tree like this, and then we come down and then we keep building it. And the max depth just tells us like how many of these, 1, 2, 3, 4. This is 4 layers. How deep can we make these? The number of sample splits. This is like the number of, would be 2 splits, but maybe this one has 3 splits. So how many splits are we allowing at each step? Okay, I'm not going to keep going through these, but the idea with hyperparameter optimization is we want a way of learning these. These have an impact on how the model is able to learn data. And so changing these will change the accuracy of our model. And so we need a way of figuring out the correct hyperparameters for each different problem we're solving. And that's the process of hyperparameter optimization. And here we're doing a hyperparameter optimization over this parameter space. And even though this is very compact and looks straightforward, this explodes because now we got to say, okay, we're doing 10 plus none plus 3. That's one version of it's a grid, right? It's actually a 3-dimensional grid. We could picture it as a giant list of numbers, and this is one, and then that's another, and then that's another, and now we go to this, and that's one. You know how this works. You know the game. Then there's this one, and then this one, and then that one, and so on and so forth. So this really blows up. And I run this as an example. Let's do that. So I actually plug this in, and we use something called grid search CV right here. And why this line right here, this took a while to run on my computer. I think this took a little while, even though we're just using this iris sample data set. I'm pretty sure this was still kind of slow because grid search CV with 3 means for each of these combinations, we're actually training 3 different models. We're using k-fold cross validation with k equal to 3. That's why I set it low, right? You might want to do 5 or something, but it's going to be really slow because then for each of these combinations, we train 3 different models and we, calculate some accuracies. That part's easy. It's the training that takes a long time. Welcome to the ML tools and frameworks lesson. We're going to talk a lot about MLOps in this. There's a cool podcast. It's called the MLOps podcast, I guess. It inspired me a lot. For many years, I was thinking about becoming like an MLOps engineer. That was my goal because it's super cool what you get to do. You get to do infrastructure management, setting up and maintaining machine learning infrastructure, cloud resources, lots of cloud stuff, building pipelines to do data processing, model training, deployment. I do a lot of this stuff. I get to do a lot of this stuff in my work, but I'm not an MLOps engineer, technically. But model monitoring. So this is something that monitor performance, detecting drift. This is something I don't get to do a lot of in my work because we don't have serious production models like an MLOps engineer would be probably in charge of running. If a company is willing to hire you as an MLOps engineer, you've probably got some pretty serious models that need to be tracked and looked at very closely. Bunch of examples. Oh my God. Setting up CI, monitoring model performance in production, cloud computing, feature stores. That's a whole thing. How to storing data in a feature store. BigQuery could be a feature store. Just store a bunch of data in there. data versioning, developing models serving APIs, building actual APIs to serve these things, or doing that with cloud services. Okay, so there's tools to help MLOps engineers. And MLflow is one that's open source. It's an open source platform, manages the whole life cycle. Here's an example with scikit-learn, like we've been seeing, but we plug in an MLflow experiment. This by using this context, Python has these contexts. So when you do with something, anything running inside of here is now inside of the context of this, which means there's certain things available that are kind of hidden. They're kind of in the global namespace of this context. So when we call something like mlflow.scikit-learn.log model, we can kind of inject some metadata or some sort of data about this particular run into here. It's a little tricky. It's kind of hidden. I do like with statements where we say, anyway, it's kind of an abstraction that is kind of cool with Python, but a little bit tricky because there's some hidden stuff. And none of that matters. What really just I'm trying to say is this is how you use MLflow. And then you can do stuff like logging metrics. So here we're logging the model itself. Yeah, and here we're logging the accuracy of the model as well. So this stuff gets logged to MLflow, and then we can like track stuff, do experiments. Now we get to talk about neural networks. Have a look at this beautiful neural network. And this is literally an example that we go through. And in the lesson, you'll see a lot more detail than you will in these slides. But we're going to actually do this. And the math for this just looks crazy. I don't know what I was thinking designing a neural network this complicated for a course like this. It was sort of psychotic. In this lesson, we're also going to cover the perceptron. We're going to start from the like basics of neural networks. And this is where it all came from, this perceptron. Let's see the math for that. Here it is. Now, the original 1958 perceptron, I think, didn't exactly look like this, but this is like the modern perceptron, which is, I don't know, it's like a modern expression of it. I guess it was a little bit different, but this is what I was describing, a weighted sum, and then it goes through an activation function like this. This is the perceptron right here. The weighted sum thing, what is this, right? It's a linear model. It's just like linear regression. You get like, yeah, it's just a linear model. So the weights, these are like the parameters of our model. The X, these are our feature values. And then we have a bias, an offset term. And this outputs a scalar value. And it'll be some scalar value, like, I don't know, just something, right? It could be anything, actually, anything whatsoever. But it's a single number. That's what I want you to focus on. And then we pass that through this. And we're like, well, if that single number is above 0, we're just going to call it 1. But if that number is below 0, we're going to call it 0. Okay, and then there's another thing. There's a learning rule. So the trick is we want to learn these W's, and so we get a little bit of a learning rule, and that looks like this. And we want to gradually update the W's based on some sort of rule here, which is described by this. And so it's like the difference is how we want to get closer back to these labels. So we look at these small changes. This N is like this learning rate. We want to just like push the model towards making better predictions. And so this is how we do it with this learning rule. You know, assuming I didn't screw this formula up, because honestly, I'm not sure where this comes from. I think it's some sort of derivative of the error, right? This is kind of like a gradient type term, but I'm not showing where that comes from. Okay. Now we're going to extend this. Oh, never mind. I'm going to implement this. Yeah. Okay. So we actually implement this in the course. Like in the lesson, you'll see a full implementation of a perceptron. And this is kind of what it looks like. We got a predict method. I am totally not going to go through this, but the point is, look at this. I'm only importing NumPy. And we implemented a perceptron just based on NumPy. There's no deep learning library, anything like that. It's just like, I don't know, 30 lines of Python code, and we've got it implemented. And then we did this with it. We literally built it and trained it. So this first example up here corresponds to when we had, let's see, this was just when we had not iterated on the weights. We just had some initial weights of our perceptron, and we hadn't trained them yet. And then we do this training process for 100 iterations, and we get this. And now we've actually learned to separate this data set. Whereas before we were not separating it correctly. We were only classifying this. This was our decision boundary. Now we have properly done it after 100 iterations. Backpropagation algorithm. this consists of first doing the forward propagation, and we go through the whole neural network and we do stuff like compute activations, and we store intermediate values and stuff like that. And then we get the error. So we're going to get the error of all of our metrics. So we have some weights, we have some biases, that's these guys, and we do the forward propagation and predict error based on these things. Then we do backwards propagation. And so we start going backwards through the network, and we iteratively update the weights and biases using these functions right here. And this is, in the previous slide I told you, we're taking the derivative of the cost function with respect to the weights, and the derivative of the cost function here with respect to the biases. And so that's these are partial derivatives. And this is how the backpropagation algorithm works. So if you want to actually see this, if you want to really understand this, I suggest working through an example. And the example I'd say to start with is right here for this beastie neural network right here. And I show you an example of backpropagating a little bit. I don't go through the entire thing, but you can see I start with the forward propagation, and then we're doing layer 3, and we're doing the backpropagation. I'm like, we perform the calculus of gradients by working backwards. We start with layer 3. This is layer 3. So we don't even get to layer 2. This is all just for layer 3. I would recommend checking that out in the article for this section. Now I'm going to move on to activation functions, and we'll complete this lesson and largely complete the deep learning section by talking about these things. And this is kind of nice because honestly, these are a lot simpler than what we were just talking about, like the backpropagation. Activation functions are not so crazy, I don't think. So we showed one activation function, which was like ReLU. We also showed the step function. We'll talk about the sigmoid function here a little bit. And what these do is, like, they're applied element-wise. So when we calculate something like this z, this is a vector, and then we dump it into this function and we get a vector out. So the assumption is we're just applying element-wise to each element in this z. They're really simple, honestly. The sigmoid function is really cool because it maps any input z into a probability, into a probabilistically interpretable output. And the functional description of this is beautiful. It has this exponential, like Euler's number, right? So E is like 2.7 kind of thing. This guy, like this is, yeah, I'm sure you know this, but this is like, I think it's like 2.71 or something like that. It's just a number. And so when you take that number and then you put z, you take z as the exponent for that. Anyway, this function outputs something between 0 and 1, and that's what we're seeing here. It's between 0 and 1 at the top. And so we get this really nice, like smooth, differentiable function, which has really nice properties from a mathematics point of view, and we can map these inputs into probabilistic outputs. And so the softmax function, we should think of that as the multi-class generalization of the sigmoid function. So it converts a vector of raw scores into a probability space that's normalized with respect to each other. Welcome to the lesson on famous neural networks. I wanted to talk about 3 particular neural network architectures, one of which is the transformer architecture. And this is what enables all this amazing LLM stuff that we're seeing. They're built on these transformer architectures. I'm going to talk very generally about this and from a conceptual point of view. This image here is taken from the Transformers paper, which is called Attention is All You Need. And this illustrates something to do with the attention heads. And here's that paper I talked about at the beginning of the video where this introduced the transformer architecture. It's called Attention is All You Need. It was in 2017. And these transformers, the interesting part I'll focus on is this self-attention mechanism. And so you can model relationships between all elements in a sequence simultaneously, regardless of their distance. So it became the foundation of models like BERT. This was the first one I heard about. And I realized we could do this. There was this Python function for summarizing text, and it just felt like magic. And that was powered by stuff like BERT, which was trained on a big data set, like a big news data set, I think. So this stands for bidirectional encoder representations from transformers. And of course, GPT, generative pre-trained transformers, is also based on this architecture. This slide is meant to talk about why transformers work really well for sequential data, in other words, text-based data. This self-attention allows them to capture long-term dependencies. And what it does is it considers how each element in the sequence relates to every other element in this sequence. So it's really good for ideas where there's these complex dependencies, like I went to the gym today and it was great. So the great refers to the gym, which is like way back in the sequence. And this attention would relate those two words together to build this semantic understanding of this sequence. Here's a conceptual example of the transformer architecture. And we're going to walk through an example of this here. I went to the. So the first thing that we'll do with the transformer architecture is to tokenize the words. And this is not embeddings, this is just tokens. So I gets mapped to 101, and went gets mapped to 4567, and then 2 gets mapped to 39. And so every single word in the whole vocabulary just gets mapped to some token, like an integer number. And then the next step is to embed those tokens. And when we do this, we also add positional vectors. This is kind of a weird thing I didn't expect at first. So when you do, you'll embed these tokens into a vector space. So like I goes into a vector like this, but then you also add these positional vectors, and that is what tells the model about the word order. These embeddings are what go into the neural network, right? It's like that's how we get the words into a numerical representation to start feeding through. And then they're fed through all of these different layers. And at this point, I'll mention there's I think it's called 3 green, 1 blue, or maybe it's 3 blue, 1 brown. Yeah, something like that. I'll probably know the guy I'm talking about. He's on YouTube and he makes these visualizations, and he has incredible ones for the transformer architecture. So that's kind of like required watching if you're interested in understanding how these work. So as these sequences start passing through the transformer layers, they're gradually getting changed into a richer representation that encodes more about the meaning. Like it basically endows these vectors with more semantic meaning, but also about how they interact with each other. So it creates these rich relationships between all of our different embeddings inside of here, depending on like the word order and so on. So in the final hidden layer, eventually we reach the end of the neural network after all of these after all of these like self-attention layers and all of this mechanism of the neural network, we eventually just reach a hidden layer. And this final hidden layer, inside of here, we should have generated a vector that will encode some understanding of what every token of what token should come next in the sequence, because that's the goal of the transformer, is to predict the next, or like in this architecture here, like a model like GPT implements, the idea is to generate the next token in the sequence. And so we use the final hidden layer in order to do that. And from this final hidden layer is how we project this vector to vocabulary logits, and effectively we get out a bunch of probabilities for candidate words. For example, in this case of I went to we might find that store is the best, most likely next word in the sequence based on this whatever's in the final hidden layer of this transformer architecture. That's just the next word, and now we repeat this whole process for subsequent tokens. Welcome to the data engineering section of this course. I've got 4 lessons. This is the first video lesson. I've got a whole bunch of articles on this. I went a little too hard probably on the data engineering. Data quality is a big topic in data engineering because it's really difficult and it's really important to try and get right. Otherwise, you get issues like missing values, inconsistent data, outdated information, and so on. Here's just a few topics with respect to data quality, like consistency. If you're storing data, is it in a standard format? Same with the columns, like is your data structure like are your columns consistent formats? Say you switch from like feet to meters, but you don't indicate that anywhere. That's like a format problem. But also formats could refer to like file formats. If you're storing CSVs and then you just switch to Parquet and maybe you're flopping back and forth, obviously that's a problem, right? Also duplicate data. So completeness is like, is there data? Yeah. Do we have full data? Is there missing days that can never be recovered? How about accuracy? What is the source of truth? If there's multiple sets of data, which one is the source of truth? Like what if there's different data sets that differ? Which is the one that I should trust? And timeliness, of course, is like, is the data arriving in time? If not, that's a problem. I don't know, I guess that's outdated, or I don't know what this one would be, but that's still like a data quality type issue. Real-time versus batch. So in data engineering, we could have real-time data like down here, and this would be intended to handle data as it arrives. And basically, as soon as something arrives in a place, you just handle it and push it on somewhere else. So IoT monitoring is kind of like a bit of a canonical example for this, because IoT devices are kind of just like maybe constantly sending a bunch of stuff. So you need some sort of receiving end that can just be picking that up and putting it somewhere. Fraud detection is also kind of cool, right? So you do a credit card transaction, that needs to be handled kind of like right away to detect if that's fraud, and then tell the vendor like, yes, accept the transaction, or no, do not accept that. So it's like a real-time processing is required there. Now for batch processing, this is more common, a lot more easy, a lot cheaper. So you're processing big volumes of data, not necessarily big, but just maybe not in real time. You kind of do it on some sort of job. For example, you could do a nightly model training job, or a weekly training job, or even hourly. Or there's this idea of sort of mini batches where it's maybe like once a minute or something, but it's still in a batch and not exactly real time. So what are the role of encodings? Encodings define how the data is interpreted. And encoding says, when I see data that's like this, and I'm just looking at this thing, and I'm a computer and I'm just looking at this data, this means nothing to me. Like until I know the encoding, this is just like, okay, well, I just see a bunch of numbers, dude, but like encodings tell us how we map these numbers into the things that we see, be it text, be it images, or be it videos. We need an encoding to translate between binary language and between objects, properly interpretable objects. In other words, when we load this binary data into a file, there's no like one rule to say how that should be interpreted as an object. Instead, we need the encoding. Like maybe we say, okay, well, this is UTF-8. And now we're like, oh, okay, well, if that's UTF-8, then I know this chunk here represents A. And then this chunk here, I know that represents C. And so we can start piecing together what it actually means. But if we don't know the encoding, we can't generally do that. And that leads to like encoding issues. When we get it wrong and then stuff starts looking funky and we're getting like the wrong characters, it's because we're misinterpreting the binary data. So, okay, that's cool. So let's talk more about encodings. CSV and JSON use text encodings, something like UTF-8. This is a visualization of the modern data stack, or like some concepts in the modern data stack. Here's a bunch of stuff on data storage. And some examples of data storage techniques are like a data warehouse. In my day job, I use BigQuery. I've messed around with Snowflake a bit. Snowflake is kind of a weird one because actually you might want to do data lake stuff on Snowflake. And so data lakes are super cool, probably out of the scope of this course, but basically a bunch of files in S3. So instead of a database where it's all like just data managed by the data platform, you're like, no, I just have a bunch of files in S3 and that's my data lake. And now let me get Snowflake to talk about that. And now here's a ridiculously simple example after all that complex stuff of, okay, we've got source data. Let's load it through Fivetran. Now it's in a Snowflake database. We can transform that data using dbt, and the final output is Tableau, where users can now explore this Fivetran data that has been, enriched somehow through some dbt transformations. And the key part about this slide is this is not happening once. This is constantly happening. This is a loop that, data keeps flowing through here. So it's always current and it's always live. And that is kind of the catch with data engineering. It's like, you're not just doing this once. It's always got to be going. It's always got to be live.
Here we're going to compare ETL with ELT. So ETL is the traditional approach to data pipelines, and we extract, then transform, then load. And in the extract phase, we're pulling data from source systems. Could be stuff like databases. So for example, you could have a transactional database where you just have a bunch of records, and every time someone makes a purchase, they get added to that database. Or you could have an API, or maybe there's a bunch of flat files like in cloud storage or something. So this is our extraction phase. Then we want to transform. And in this phase, data is cleaned, it's formatted, it's enriched, and this is being done before it's loaded. That's the idea with ELT, is you transform the data before you load it into your source, into your target database, into your downstream database, your data warehouse. And this is going to be something that should be optimized for analytics use cases, for that's my thinking, at least, is like we would want to put it somewhere where now we can consume it in like a dashboard or for analytics or something like that. This is my view in ETL. When it comes to ELT, we switch the step of load and transform. So it's a modern alternative because cloud-based data warehouses are really good at transforming data. So rather than like transforming it in the process of getting it into the database, it's more efficient nowadays to just pull it into the database. And then once it's in there, and this is not a rule, like it's not like only ELT works nowadays. I do a lot of ETL stuff in my data pipelines, but the basic idea is like once it's in this scalable system, for example, I use Redshift data warehouse, or maybe you're using S3, these flat files, and you just have a bunch of data in S3. Now you can transform it. So you could use like your platform, like Snowflake or BigQuery or Redshift or whatever, to actually do the transformation in there. You're using the compute and processing power of the data warehouse itself. In terms of data access and delivery, I've created this absolutely ridiculous chart. The whole point of everything we've been talking about is kind of just like to make your data available for someone to use it. In doing that, in making data available, there are lots of considerations. And this chart is kind of the security style implications of that. Of course, there's error handling. If things go wrong, we need to be handling that. There's access management. Who can look at the data using best practices, like the principle of least privilege. So if you have an application that needs to look at some data, don't let it look at your entire cloud infrastructure. Just let it look at the exact data that it needs. Ideally, you want to use the principle of least privilege, even though this does take a lot of time. It's a lot easier to create a single API key that just lets you look at every single thing and use that API key everywhere. But that's bad, and bad practice, because it's a security vulnerability. Okay, monitor and logging is a consideration so that we can audit and just keep an eye on stuff like costs. We want to set up cost alerts. API security, this is more straightforward. It's within the API. So if you're exposing your data through an API, you should use HTTPS, so data is encrypted. You should use API keys or OAuth if you're super serious about it. But even like stuff like putting these in the headers rather than the URL string or whatever. Okay, and then data encryption. So with cloud data warehouses, data is usually encrypted, both at rest and in transit. But if you're spinning up your own Postgres database on some random server, that's probably not going to happen. So understanding that. And then there's compliance stuff, GDPR regulations in Europe. If you're like customers have certain rights and you can't store certain things without asking about it. And then lastly, network security, like firewalls, not exposing stuff, not screwing up the network. Basically, is your database publicly readable? If so, you put a firewall up. Don't let that happen. Or even just like limiting stuff. Well, there's also internal networks that companies use. So virtual private networks. VPNs, yeah, but not like a VPN like I might use to, just like change my Netflix location or something. It's called like it's like a network that enterprises have set up where like only they can access that stuff through the network and nobody else can from the outside world. But also you can do lots of stuff with networking security. There's also lots of little gotchas. For example, with using Docker, which can expose stuff past firewalls, and you have to be careful of that. Welcome to the databases lesson. This chart has a view of a bunch of different database styles. Here's a bunch of SQL concepts. Here is a bunch of NoSQL concepts. And then vector database concepts. These are important for embeddings, for storing and accessing embeddings. And then there's a bunch of other type of specialized databases. Now, certainly a vector database is a type of specialized database. It just turns out to be so important for AI applications that we're going to talk specifically about this. But you should know that there's a bunch of different types of databases for kind of every different thing you might want to do, like time series analysis. You can use graph databases for certain things like social networks or something. With that said, let's get started. And I can't emphasize enough how important SQL is for data jobs. I highly encourage you to play with SQL and learn it, and always invest into understanding the examples that are presented to you for SQL. Which I don't know if we'll actually see any, because this lesson here is more about like concepts behind SQL. Let's start up here. There's two different types of workloads that SQL engines can accomplish. We could have online transaction processing. MySQL is an example of an OLTP style database. Good application for this is you've got user data on a website and you want to keep adding stuff, or users upload images and so you add that, or metadata, or people make purchases and so you add each purchase to this database. The OLAP database is for analytics, and it's like we have a bunch of this stuff. Let's put it into an OLAP style database so that we can run queries on it. We can select the counts and averages and means and customer data and hook this up to a database and do machine learning. That's the purpose of OLAP. Generally, this is row oriented and this is column oriented. Now we're moving on to the third database we'll talk about in this video, which is vector databases. These things are for managing embeddings, which are becoming increasingly important in the context of AI. Let's look at an example here, a vector similarity search. In this use case, we want to find vectors, i.e. embeddings, that are most similar to a given query vector. And this is kind of like, in my mind at least, this is like the 99% of vector databases are trying to solve this problem right here. And so we use metrics we've talked about earlier, like the cosine similarity. And the idea with vector databases is that they can handle billions of vectors, like tons and tons and tons of data for large-scale AI applications. This chart here just generally indicates two different flows. This is one flow on the left, and then the other workflow is when we actually want to run a query, and that's kind of this one right here. So starting with the green, we get some new data. We pre-process that. For example, we could chunk it out and then embed each chunk. That's the generate embeddings part. And then we put that into the vector database. That's like in ingesting. And this might be an upsert style operation. So maybe this data is actually already in the database. We kind of just want to update it or replace it kind of thing. The other workflow is for when we have an incoming query. So now we have this vector database full of stuff, and now we want to match that. We want to find out the matching chunks based on some query. So we embed that query, whatever like the user wrote, or the chunks, like the interesting part of it or something. And then we run a search, and we're saying, like, let's compare that query to all of these embeddings inside of the database using this vector index. And this is the part, this sort of final part right here is where like vector databases use a lot of specialized technology in order to do this fast at scale, handling billions of vectors. Like, this is not a trivial thing to do, and it's also, there's trade-offs as well in here. So we'll talk about some algorithms like that are used for that later. We're talking about data orchestration, which refers to the automated scheduling, monitoring, and execution of interconnected tasks in a data pipeline. And there's specific MLOps tools for machine learning data orchestration, but here I'm just talking about general use tools. And I'm going to focus highly on Airflow. This is the tool I use for my data orchestration. So here's an example. Airflow is open source. I run this for free. Like, I just use the open source software, and I installed it on a server. And this lets me author, monitor, and schedule workflows using these things called DAGs. This is a really simple example of a DAG that's going to execute every day at 1 a.m. based on this cron schedule. And it runs two functions. It has this extract function and it has this process function. And the way that it's been set up is through these dependencies down here. So first, we're going to execute this extract task. And once that's done, that's what these indicate. Once that's done,
we'll do the process task in that order. And if this task fails, we won't get to the process task because the downstream task has failed. And this gives us lots of monitoring and visibility into how this is working. We also get to define things like retries. We also can define stuff like the start date, and then this will automatically start backfilling and run for every date going back to the start date, unless you configure it to, for example, don't backfill. And there's some sort of nuance around there, but this is the basic idea, and I find it very intuitive. Welcome to the AI engineering part of the course. This is the first lesson where we're talking about some introductory concepts and general ideas in generative models, like LLMs. And if you've got here all the way through all of the math and deep learning and statistics and machine learning and all this stuff, then congratulations on making it through all of these foundational topics, which we've gone through in depth and discussed at length. And if you've skipped over some of that stuff, that's still totally fine. I'm going to try and teach you a lot of stuff about LLMs here in this set of lessons. Context windows determine how much text the LLM can see at a time. And converting tokens between text, we can use this ratio of 0.75 words per token, or alternatively 1.33 tokens per word. So inflate the number of words by 33%, and you'll roughly get how many tokens that we're talking about. Another LLM thing is temperature settings and sampling strategies. The temperature determines the sampling Okay, so sampling strategies is different. An example of that is top K sampling here. Let's first talk about temperature, and that's what I'm showing here. So a low temperature would make the output more deterministic. An example of a low temperature is this one right here. And along the x-axis right here, each of these are a different word. So this is the first word, second, third, fourth, fifth, and we're trying to predict the next word. So with a really low temperature in this example, this is real data. I think it's from GPT-2 or GPT-2. And up here we have like a 60% chance with temperature of 0.1 of picking the first word, the most likely next token in the sequence. And if we put that temperature all the way up, so here now a temperature of 1, it corresponds to this one. We have a temperature of 1, and now the first word has only a 6% chance. It's gone down 10% of what it was. So it's only a 6% chance of getting the first word, and we're much more likely to actually now pick one of the other options with a higher temperature. And as we continue to raise the temperature, we continue to get higher probabilities of these of other ideas. And so it's increasing the amount of randomness in our generation. Now let's look at the other idea, the idea of sampling strategies. And so down here, I have a top K sampling strategy. And so in this one, we would select the top K most likely words and then only randomly sample from those ones. So for example, what I'm saying is you take only this slice and then do the random sampling in there. Of course, for temperature of 0.1, this isn't really interesting because we're pretty much guaranteed to get something in there. But now for one of these higher temperature settings, that means we get to exclude everything to the right and we just sample within these top 3. So that can be helpful for including randomness, but constraining it to be only like realistic type options. The final topic in this video is fine-tuning. This allows you to adapt a model, take a highly versatile model and adapt it to your unique needs. The way that this is done is by updating the model weights. You change the model weights or somehow affect them in order to, customize the outputs to be what you're looking for. And there's a lot of technical jargon here, like activate the right latent space. Kind of like, let's try and simplify this in the following slides and explain what fine-tuning is all about. It's the process of taking a pre-trained model and further training it. That pretty much makes sense. We have like a whole bunch of weights, all these weights, and we're going to sort of start tweaking them around. We're going to continue the training process, and we're going to do this on our specific data set in order to adapt its behavior. So I want to have an example. I mean, okay, down here, I'm like, you can just do this. Like, this isn't some abstract thing that you need a lot of machinery for. You can do this by just like taking JSON files and like dragging them into the OpenAI platform. And you can actually like create your own custom models and call those through the API. OpenAI is leading the way. Like it's the go-to thing if you want to do fine tuning right now. And you should do this. Like log on there and play around with this just to really get your hands on it and understand. So fine tuning is really difficult because we're changing many model weights. And so it's like from an engineering perspective, it's complicated. From a cost perspective, it could also be a problem, but it's very efficient relative to training a new model. Training GPT from scratch, as everybody knows, is an incredibly difficult and costly task, but tuning its parameters is actually obviously much more efficient. So challenges with fine-tuning, hallucinations, all of these things can be mitigated, but they're all just things that we need to think about. In terms of resource constraints, I've talked about how OpenAI abstracts a lot of these things, but if you were trying to do this yourself, it's going to be very difficult. There's also a data bias concern where you're training, you're doing the fine-tuning on your own data set. And so you can introduce bias into the model if your data isn't complete. So the mitigation is just have good training data. Same considerations as any machine learning problem. Welcome to the embeddings lesson. We're going to get to this visualization example soon. And what embeddings allow us to do is to take strings and put them into some sort of numeric space. And the idea is to capture the semantic meaning of a word using numbers. The embedding space, a good embedding space will reflect some semantic understanding of all of the text. Embeddings are learnable. Models create embeddings, so they need to be learnable and they need to be optimized for specific tasks or domains. And OpenAI provides general purpose embedding models that we can use. And in that sense, they're transferable. So pre-trained embeddings that are provided by, for example, OpenAI can be reused across different applications. Vector embeddings have incredible applications in the world. And a cool one that's not even on this slide is Spotify. So Spotify will embed all of the different songs. They'll create vector embeddings for the songs, and then they can really quickly find similar songs based on any given song. They can find the matching vector embeddings, the most similar songs to that one. It's part of how Spotify works. But search engines use these. They've been doing it for a long time to understand semantically information. Recommendation systems use these. I just mentioned Spotify's, but Netflix would also use this. And sentiment analysis uses this. Like you can analyze customer feedback to determine the semantic understanding of these strings. The basics of embedding search we have already talked about a lot. It's basically cosine similarity. I'm going to skip this slide. I think we know that. This slide we'll talk about again. We'll revisit cosine similarity, which we talked about in the mathematics section. This is the formula. It's just getting the cosine of an angle. When doing embedding search at scale, the simplest approach is to iterate over every vector in the data set and calculate the similarity metric for each. That's what I'm showing in this sentence right here, where we're calculating scores by iterating over all the dataset vectors and getting the cosine similarity between what we're looking for and all of those. We're looking for this in this case. This is our query vector. But this goes as order n, which is not going to work for us. As we get to really big data set sizes, this is completely impractical. So we need alternative solutions, and ANNs are one of those solutions. And here I actually implement that. So I'm using the Python library for Facebook AI similarity search. I create some sample data set, and then I ingest that into a local, into memory. I basically ingest this into a local vector database inside of my computer's memory. That's what's happening here. So in a real system, this is the line here where your computer freaks out and takes forever to process and then gets a memory error, because it's like just putting everything into memory. All of this stuff just goes into memory here. But once we have this, we can do searching on it. And so I do some of that searching here. We generate some random query vector, and then I say index.search. I search for that actual query. I find the top 5 nearest neighbors, and then I plot it. And this is the plot that I generated, and this is the result of all this code on the left. It's actually this plot right here, where we can find all the nearest neighbors to the query. And I will call out, this is a PCA projection. So the actual embedding space that we're using here is much bigger than just 3 dimensions. but I take the PCA three-dimensional projection, and that's how I generated all these data points right here. Welcome to the video on RAG. Doing retrieval augmented generation, unsurprisingly, has two aspects to it: retrieval and generation. And the retrieval aspect is a natural extension of this embedding stuff, which we've just been talking about. Here's a visualization of some query vector here, and in the retrieval aspect of this system, we're going to get all of these points right here, all the most relevant context to that query, and then pull those in, and then get a generation based on that. That's the basic idea with RAG. Now, some practical considerations around RAG are with respect to document processing and document chunking. When we process documents, we got to decide how to chunk these things out. And if you do anything with RAG, you'll pretty quickly realize, okay, I got to pick a chunk size, and I have to pick some other stuff like an overlap strategy. I also have to think about metadata. So for each chunk, what do I want to actually track in that? Like, I probably want to track some idea of the relationship between that chunk and previous ones. And metadata I'm picturing as a JSON object. So picture like a JSON thing with a bunch of keys and values that kind of just tell you, okay, so for this chunk, which by the way, the chunk is just, it's an embedding. It's just a bunch of numbers. We're like, I don't know. It's just a bunch of numbers. What do you want from me? Well, that's what the metadata is for. It's like, okay, no. Look, so for that bunch of numbers, this is all of the actual, like, that's what's going on with those numbers. Like, this is where it comes from. This is the next one. And that could be obviously very helpful. Practical implications of this, we want to retain semantic coherence between the chunks. So we want to keep our chunks big enough. Like, maybe we could break them at natural boundaries, like paragraphs or sections. And that's also what the overlap does. It helps make sure that we have this like logical completeness. It helps preventing loss, like between the chunks. So say we have a boundary where there's a clear semantic topic, but then it's covered in two chunks. Well, we would, the overlapping just kind of helps us ensure that we're not like missing that whole semantic topic. Maybe this is the most relevant chunk and these two are good, but maybe this is really the chunk we're looking for. I would recommend taking your exact problem, plugging it into language models and getting them to advise you on what they think the best sizes are for you based on your database, based on your data, your use case, and everything like that. But a typical range, something we might expect, would be like 100 to 1,000 tokens, where if we convert this back to words, we're talking about like somewhere around 500 words. Welcome to the video on agents. Agentic architectures are an important trend recently in AI, and going into the future, agents are going to provide a ton of value for end users. And building agents is also pretty fun, but it's complicated. This is an example with LangGraph, and we're going to talk through some LangGraph examples in this, but more generally, this lesson focuses on higher level concepts. I'll talk more about why that's the case, particularly with the rapid pace that these things are evolving and not showing you too much legacy code that won't be relevant anymore. I'll show you what I mean. A good agentic pattern to get started with, specifically with seeing an actual LangGraph implementation, is a router agent. And these guys make simple step-by-step decisions using these sort of predefined options. This is the basic idea of a router agent. So we're going to start with some user prompt that's going to trigger the beginning of this workflow. And in this case, it's like, I want to go on vacation, but I only have $500. And this is how we start our agent. We kind of seed it with this human message. And then it's going to take that and go do some stuff. And the thing it's going to do is make a decision. It's either going to go on path A or it's going to go on path B. And whatever decision it makes, that will be the end of the agentic loop. So walking through this actual example, now I need to mention LangGraph here, like the actual details of this example will change as LangGraph evolves. And this stuff might not work in future versions of LangGraph. In fact, I don't expect it to work because of the way that LangGraph and LangChain and AI in general is evolving. However, the basic concept here remains the same. I want to stress that, but I do also want to walk through this example completely. Also, last note on this, it's not that this will stop working on the current version of LangGraph. Like, this is pegged to some LangChain, LangGraph examples, some specific libraries which you can install. And for the next few years, presumably you'd be able to still install these, but they'd be legacy versions, so they wouldn't support the current functionality. And so you probably wouldn't want to do that. You would probably be better off looking up online the recent documentation and writing this how things are done So if it's 2027 and you're taking this course, it's probably going to look a little bit different. Now, let's walk through this example. First, we're creating a workflow, a graph, an empty graph, nothing's going on here, and then we define some nodes. And now this graph is full of life. It's actually got all these nodes, but we don't have connections between these nodes. These nodes kind of have no understanding of each other. And so we got to start adding edges. So here's an edge from start to decision. And so we go from start to decision, and that creates that edge for us. Now we have another edge here. It's a conditional edge. It's from decision to this route decision function. So it's going from decision, but now, well, I don't know what we're doing. So this route decision function is what is going to kind of decide somehow where to go next. And then I add these edges called path A and path B to end. So this one here, I've defined these two edges. So these two are defined. And what else was defined? This one's defined, but this middle step is a little weird. Like we don't exactly know what's happening. Somehow we're doing that right here with this one. I'm going to explain this by showing you what these functions are in the next slide. But first, I want to just continue walking through this full example. And the last thing that we do is compile our workflow. So in LangGraph, it looks like this. We say workflow.compile, and then we can run this graph. And we can say graph.invoke, and this is how we start our agent. We sort of trigger it off by invoking it, and it goes off and does its stuff, and it's going to provide some response. This response object right here will come back and will fetch the content from this messages. So this response object is going to have all the data, all the outputs of whatever this agent did for us. Now, I think this is still a bit confusing. So the next slide, I'm actually breaking it down what this thing is doing in terms of the functions. And I have this full example and written out in the course in the article. It might be more clear to follow there, but let's walk through it again. Welcome to the MCP lesson. Model Context Protocol has been the most interesting thing in AI that I've got to work on in the last year. I'm kind of obsessed with it, and I had a lot of fun building this lesson. I have a lot of fun building MCP servers. I've built 3 of them at time of filming, and I know there's more to come. And I mean 3 on PyPI, open source. You can download them, try them out, and so on. It's really fun. So this lesson is definitely a prerequisite for if you want to build MCP servers. It's also important if you want to use them in any capacity to understand how they work. And I'm going to explain all of this with the fundamentals in architecture. Then we're going to have some hands-on demo of using these things and then building these things. And in the articles for this, I will refrain from mentioning this again, but I go through all of this in detail, and the idea is that you'll follow along with me and actually be doing these things like hands-on tutorial style stuff. So I highly encourage you to go and follow through with the articles after watching this video. MCP is an open standard for AI systems. It's a protocol. So the protocol means it's like HTTP or TCP in the sense that it defines how data is transferred. And the data we're interested in is stuff that allows us to do tool calling, so sending data to tools and receiving data back from those tools, and also resources, so accessing data, just like asking for external data and receiving external data. But this protocol part is something that's very important. It's a standard, and it's also a protocol. And when you combine those two things together, you get something like MCP that defines how data should be passed. Similar to HTTP, similar to TCP. When an MCP call is made, like when you ask this question, what's the weather like in Toronto? The MCP client, this was like Claude Desktop or Gemini or Cursor or whatever, requests weather data. They send it a piece of information. So that's this one. It generates this request, this JSON object, and it sends it over, say, standard input output or streamable HTTP over to the server. Now next, so this is, okay, let's look at this. So it's like, what was the weather in Toronto? It figured out, okay, we want to do a tool call. It prepared this object, looks like this. It has an ID. It defines the method. It has a method here. And then the method of transport, this JSON RPC 2.0. And then down here, it sets the name. This is all the information needed for the tool call. So this is the name of the tool we're calling. And these are the arguments. And this was up to the client to figure out how to generate this and fire it off to the server. And the server will receive this message, and it will do its tool call calling, it'll process this, and it'll send back a message that looks something like this. It'll have some content, and text in here will have the output, the result of that MCP call. This will then get picked up, and the LLM can continue its work with this new data, this stuff that it got back. In addition to creating MCP servers, which you will see a lot about in general all over the internet, you can also create MCP clients. And these things are done like this. So here we're using the MCP like library, just the client library provided by the MCP SDK. And it provides a way of doing this, an abstraction that we can use with Python like I'm showing here. And these clients can basically spin up these servers. So this is a command, this is a function right here that will connect to the Context7 server using a Python script. So when we run this script, it's going to actually spin up the Context7 MCP server using this command. It's going to start serving this thing. And this is like how Claude Desktop or how other MCP clients are working under the hood. They have stuff like this that are using libraries like this that are spinning these things up for us. If you want to follow along with this tutorial, which I highly recommend you do, you can clone my season 2 repository using this URL. It's like my YouTube season 2 stuff, all of the source code from my season 2. But inside of there, you'll find this MCP tutorial folder, and you can hop in there and explore exactly what's going on here. It's a full proper MCP server, which has a pyproject.toml. And so when you run uv.sync, it'll go ahead and install these dependencies on your computer. And once that's installed, we'll do uv run fast MCP tutorial. This is also defined somewhere in the pyproject.toml. That's why this works. It's a script that we define in here. And once we do that, it starts serving it. And you'll just see it outputting in your terminal. But this is going to be highly useless. Like, it's not going to do really anything. You're just going to want to make sure it works. But you can use MCP Model Context Protocol Inspector to actually sort of mess around with this. Or you can go ahead and plug this into Claude Desktop or anything and sort of mess around with it. Welcome to the AI deployment and productionization part of the course. And I'm going to talk about a lot of different aspects of deploying applications in general, and specifically applying that to language model applications. The more serverless it is, the more the cloud platform manages those things. An example of not a serverless architecture would be EC2. And this would be a server that you're managing. You decide how big it's going to be. You have to secure this thing. You have to, so it's more difficult. And the security is a big consideration here, because serverless offerings can be more secure because they're easier to secure than when you have your own server that you need to manage what's coming in and out of this thing yourself. Another consideration is cost. And there's trade-offs here in the sense that if you buy a server, you're paying for it all the time, as long as it's on, unless you're like spinning it up and spinning it down, but you pay for it whenever it's running. But with the serverless stuff, maybe it ends up being cheaper because you don't really pay for it unless you're using it. So if someone only runs your AWS Lambda like once a month, that'll pretty much be free for you to run, whereas you'd have to be paying for a server potentially all month just to run that function. On the other hand, as you scale, EC2 can be a lot more cost effective, and there's other trade-offs around serverless architectures. Here's a RESTful API, very practical example. It's using Fast API. This is my preferred way of doing API stuff nowadays. So what we do is load a model. We're loading this from memory. This is a binary. It's stored in a binary object called a pickle object. So we load this. This might take some time, but this is only done when we first start the API. Then it loads and it's in memory of the computer of whatever's running this API. Then we initialize the API and define a route. And now this route is available, and we can request stuff from this predict route using a post request. And when we do that, we want to send data. And the data should look like this, and we're going to pass that in as a data object as part of our post HTTP request, and it better have features in it. This is going to specify, this is Fast API's way of saying, make sure you include a list of numbers inside of this features key inside of your data that you pass. And because that's guaranteed to happen, it'll throw an error. If we don't have that, we can just run this without even, necessarily validating. This is going to do the validation when we get the post request. That's one thing that Fast API helps with. It's kind of like higher level API stuff. as well as giving this really just nice Python SDK interface to be able to create this. So we get our features, and then we generate a prediction using a line like this, and we return that prediction as this dictionary object. This gets packaged up and sent in the response to the user. So when you ask for a prediction and you send in data like this, you get back this data right here. And what you would do is you would say your response, you would get it. So we might call that response, and then we could call .json in Python. And when we call this JSON, it's a function and it's a callable. And when we call that, we're going to parse this. We're going to say, whatever you just gave me, I think it's a string, but I think it's JSON. I'm pretty sure it should be JSON. So let me just parse that out. If it's not JSON, if we just returned a plain string, this will fail. But if otherwise, we're able to just parse this out and get this as an object like we want to do. Docker is the most popular tool for running managed containers. It's kind of eaten the world. So here's a basic example of a Docker file and how to run that. Here's the Docker file itself. We're importing from Python 3.9, and we use this Slim. So it's like a more minimal version of this operating system that doesn't have maybe as many dependencies as other options with Python 3.9. And there's different types. There's like different options depending on what you need. But in general, like you shouldn't use more than you need. So start from that image and then do some stuff like we're importing data into that container. And this is like actually bundling that up into the container that will get shipped. Like if you were to publish this, all of this data, this model and stuff is going to be part of that image, the data. So it'll make it really big if you're copying a bunch of stuff into it. And in this case, we're installing the requirements. This is a really common pattern that we'll see. And then we're running a Python application. And so when we run this, eventually, when we run this container, it'll actually run this Python application right here. But when we build it, it'll do the rest of the stuff. So all of this whole part that we've seen right here, this all gets done at build time. When we do the build, it'll copy all this stuff in and install these dependencies. And the final result of this guy is that we'll have a containerized environment for an API. So we're imagining this app as an API, and we're going to have that available. So as soon as this runs, this has now been made available on the local system with this application at this port 5000. Now this expose command, this is just an instruction. Like this is not actually exposing anything. It's just kind of flagging to the user, hey, by the way, what we're about to do is going to expose this, but it's not required. So you can still run applications that expose ports, even if you don't say expose here in the Docker file. So be careful of that. That's a gotcha. When you expose a port, like if we did this and we have something running on a local host, we need to put up a firewall to block that or ensure somehow that that's blocked on the server if we were running this not on our local computer. Welcome to the LLM integration patterns lesson. Here's an example of the type of stuff we'll be talking about. A user submits a prompt and the application passes that on to an LLM API. So this thing could be like ChatGPT or Anthropic or something like that. And we're going to stream some data back. It's going to start streaming data back to the client app, which is going to start rendering that to the user. And then this keeps going and this keeps rendering. And then we finally have the user gets their data back. And so this is a very common integration pattern that we'll see where the client app is kind of mediating this interaction between the user and the LLM app, which is doing a streaming operation. And building these sort of systems is generally complicated, especially with streaming. But that's good news for us as AI engineer type people, because we can get paid to do this stuff. And when you use OpenAI, it's going to automatically look for an API key called OpenAI API key. So if that's in your environment, it's going to automatically pick that up and use that to authenticate you. If it's not in your environment, you could load it, for example, by doing something like this. But now you're exposing a string that is your API key in your app. Never do that. Of course, you could call it something else and then use this pattern. Whatever we're showing here is totally fine. This is good. We're happy to do this because this is not exposed. We're just being like, well, I defined this API key, so let's just load that as the OpenAI API key. Totally fine. But if this becomes a string and we literally insert the API key into the code, that's a no-go. Never, ever do that. And even better, for production environments, there's more secure secret management services like AWS Secrets. Docker has a secrets manager you can use. And these things are more secure practices that you should consider for production applications. In terms of LLM caching, in the course article, I talk a lot about application side strategies. And it wasn't until completing writing the course that I looked back on this and I thought, this is pretty confusing because actually LLM provider caching is a lot more interesting. So I'll quickly go over the application side strategies. This is just conventional caching stuff. So you take a prompt, if we've seen it before, just cache the results to Redis, or this is an in-memory style cache. Redis is more of a database. It's also in memory, but same idea. You're just like putting it to in-memory storage, and then you store them in a database or files, and you can use them later and stuff like that. Okay, that's fine. It's just not that interesting because it's classic software engineering type patterns. This down here is interesting, this LLM provider caching, because the LLMs, for example, OpenAI, will cache the internal neural network states, and then they can reuse these for subsequent prompts in the same conversation. This is completely different from the prompting or the caching we were talking about before. And what it allows you to do is, like, say you've had a big conversation and now we're about to ask just a single little question, like, why did you say that? What that does is it bundles the whole thing up, like this whole context gets bundled up and resent off. And so what they do is they cache the neural network states that corresponded to this previous section. And that allows the providers to shorten the to reduce the complexity and shorten the time it takes them to run a response. You reduce the computational cost of actually doing the forward pass through the neural network when you've provided the new data. Ooh, yeah. So this is like a thing that they do, and then they pass that savings on to you, and they make this available with like these caching costs. So they'll say, oh, tokens cost less for cached queries, and that's what it means. Now this only kicks in when the conversation's long enough. So the conversation has to get past like a certain threshold before they bother caching stuff, because it wouldn't be smart for them to. Basically, they're going to lose money if they start caching every little conversation. They only do it once it's past some threshold, and they discard these caches very frequently. So it really is only useful when you're like having an ongoing iterative conversation. But by using, like, these costs get passed right on to you. It's just something you need to be aware of when interpreting the costs of your jobs and anticipating the costs of your jobs based on understanding how the caching works. This lesson is really important because observability is very important for production applications. You want to be able to understand why something went wrong when it stops working like it's supposed to. And you want to be able to try and detect these instances of failure before users are affected by them. Code on the right, I'm going to be showing code snippets like this just to really give a practical idea of how this actually works. This would be like a self-hosted type environment where we're doing some basic logging, but we could switch this out for like logging to Datadog, or Google Cloud has a specialized, SDK and a way of logging to those platforms. Depending on how you're deploying your thing, you'll want to log in a way that we can pick it up. We can take these logs. I suppose I should, I like this because this is how we're setting up the logger, and then the actual logger.info. This stuff won't, this is pretty boilerplate stuff. We'll just be, we'll be making logs as we do things. Here we're making a response, and then we log request completed successfully. And this log here depends on how we've set up our logger. So the idea of the logger is we want to, these are all going to get sent into files. They'll get, sent into files basically with a file handler or something like that. We want to be like saving these somehow. And then these will get sent to a database. And this database is going to be like an OLAP database. OLAP. So this will be for data processing, like for doing analytics. And then that's what can generate charts like this. And this system here is abstracted. Like, this is what Datadog does. It does this as a service. But cloud platforms, GCP, AWS, Azure, they'll all have their own logging systems that can do this for us in our applications. And we can explore those logs and create dashboards based on them. As you know, LLM providers charge based on the number of tokens, the input size, the number of input tokens, and the number of output tokens. And output tokens, I'll mention, are broken down into, the total output tokens is broken down into what you actually see as the user.
and the reasoning tokens, which can be a lot. There can be maybe a lot more reasoning tokens and then just a one sentence output, but it reasoned about it for a lot of time. All of that stuff is billed as output tokens. The input stuff is just what you typed in, plus the system message, plus maybe any context that is hanging around from other stuff, anything that gets put into that initial prompt. This was the input. And the output is this completion text plus all the reasoning that gets done in here. Now this example, unfortunately, is using the completions API. When I built the course, the responses API was not created yet. So this looks a little different. Like instead of prompt tokens, it's input tokens. And this is called output tokens. And you can also get the reasoning tokens, but the idea is exactly the same. We take the response and we parse this data out. We take that and I'm logging it into a database, which allows us to create something like this. So it's a chart over time where we can see the completion tokens that are these guys right here, these orange, and the input tokens, the prompt tokens down here. Biased responses, this gets complicated, so bias detection models can help with that. Generally, misleading or false information is really hard. We might want manual review or rely on user feedback for that. I discuss more patterns like that, more things to look for in LLM outputs, and I actually have code examples, I think, in that lesson as well. So you can check out the article for more on that. However, we're moving on to AI infrastructure. We're going to get back to Docker and deployments and cloud services. So using these generic services, we can build a full AI platform. Nothing saying that can't be done. These systems are specifically optimized for doing that better. They take common use patterns from here and they abstract them into making them easier. For example, Vertex AI has a whole RAG system where you can ingest. It has a vector database and it tries to make that really easy to do. I'm going to go through each of these. We'll start with SageMaker and I'm going to show an actual demo from each of these platforms of how you would do something on these things. SageMaker can do a lot though. It can do notebooks, it can deploy models, it has this auto ML system that it can implement, it has other built-in algorithms, it also has monitoring tools. In this example, we're going to access a model that has been deployed. So it's deployed right here at this endpoint. Whatever it's called, this is where we've deployed our model, and now we want to make a prediction and inference. We want to do something with it. And I can do that with Python. I'm using Boto 3 for an SDK to talk with SageMaker. And this payload object, this defines like what we want to get. And so I'm saying, hey, hello, SageMaker, and I want to get something out of this. So I pass this payload in down here. I dump it into the body of my endpoint request, and I'm asking for JSON, or I'm sending JSON data. That's what's here, and I'm invoking this endpoint. Let me clean all this up. So I take this SageMaker runtime, and I call on that to invoke the endpoint, and I invoke this endpoint name. And so this is just calling a managed endpoint. That's what's going on here. And then we print the response that we get back. In addition to SageMaker, Amazon has a ton of other services like Bedrock for doing stuff with foundation, like accessing LLMs. They've got this Code Whisper, AI-powered code suggestions. They have Comprehend for NLP tasks. Welcome to the final technical lesson of the course. This video is about DevOps for AI applications. So in this context of MLOps and deploying DevOps, there's an idea of continuous integration. It's a core idea of DevOps. And it says we want to automatically validate code changes. And we want to do this by testing the code when it's committed. So continuous integration will be responsible for constantly validating new code as it's being integrated. This helps catch bugs early and prevent unsafe changes. And for AI ML applications, we need to think about data pipelines and data validation and model considerations. And I'm going to talk about specific tests that you might want to do for AI and ML in the following slides. Here's an example of a CI/CD workflow. It's another GitHub Actions, which is this file right here. And this one is responsible for deploying to production. So we can see two main stages here. There's a testing stage and a deployment stage. So after our tests run, we have a Docker image which is being built on this server, and then we run tests on that Docker image.
And if this step passes, then we pass through to the deployment step, and now we're deploying with Kubernetes. So this validates that our stuff is able to work as we expect before we get to the deployment stage. That's the idea of continuous deployment, continuous integration. Finally, that leads us to the MLOps part of this video, where we're shifting into talking about specific machine learning operations considerations like model versioning, experiment tracking, pipeline automation, and model registry management. Model versioning is a concept that involves tracking metadata about the model, like the dataset version that it was trained on, or the model architecture itself, and the hyperparameters. Tools like MLflow or DVC, and I'll discuss the trade-offs between these two tools and what they are. These tools allow us to do this model versioning in the context of an experiment. We've finally made it to the last section of the course, and I've got 3 more videos for you. This one's a quick one, and I had to stick this in somewhere because ethics is a really important topic in AI, in data, in general, ethics really important. The reason why being responsible with data is really important is because it ties back to people. So when there's a data leak, this affects an individual's life. Or when a machine learning model makes a prediction, that's going to affect some outcome for an individual. Like, will you get a loan approved or not, is a real thing that affects a real person. And if we're not doing this in a responsible way, then people are affected due to maybe poor modeling choices or ways that the AI systems are acting that aren't in line with like common human ethical considerations. I think that's the basic point here. Models tend to reflect and amplify biases that are present in the training data. If our training data represents some sort of bias, any sort of bias whatsoever, this can result in unfair outcomes. One example is maybe we have, I like trying to make these things really concrete. I like the healthcare example, lower diagnostic accuracy for elderly patients. Why might that be the case? Because there might be less representation of elderly patients in the training data set. So therefore, the accuracy for those patients goes down. What is the mitigation for this? We need to be looking at the accuracy within each segment. So by properly tracking the accuracy within each segment of our data that we're interested in, we can be able to tune our model to be more fair towards each segment of the data. Here's some practical considerations, things to kind of worry about around privacy and data. Data exposure is when there's a breach in the data system which can reveal sensitive data. Model exploitation is when people can use the openly available models in order to probe them and figure out how the underlying data looks, like membership inference, or you can, effectively these are attacks by extracting training data from the final model. And in terms of LLMs, these things are generative models and they could output sensitive data. Generative AI applications are affecting so many different parts of the economy. And in this video, I'll talk about some ways, some industries that are currently being almost totally reshaped by these things. Software development comes to being front of mind. Content creation is coming, but it's just not quite there yet. But we're already seeing lots of this. This quote from Stewart Brand is something I think about all the time when it comes to AI. When a new technology rolls over you, if you're not part of the steamroller, you're part of the road. And right now, the world is being rolled over by generative AI. So for me, I want to be part of the rolling aspect of that. And yes, this lesson does get a little bit dark. Returning back to the mind map, which we were talking about at the outset of this lesson, and as we see these all get better, I think we'll see more integrations between these two things, between all of these as well. So we'll see just crazy AI generated content everywhere. So this is the dark part, I think, of the talk. The education space is particularly interesting to me. I would have loved to have ChatGPT when I was back in school to explain these concepts, to understand things. I see these LLMs as a learning tool that can be good and bad, right? The bad is when we're using them without thinking about the results, and it's like a copy and paste deal. The good is when we're using them to interrogate the results. So, for example, you see the solution to your test, And now you could feed that into ChatGPT and get it to explain and walk through the test that you did and explain all of the solutions as if you went into a professor's office and they were walking through the whole thing and giving you this personalized lesson. Like, that's the future of education, and it's incredible and it's personalized, which is amazing. So I think people are going to become a lot smarter, faster through this personalized education. I included space exploration. And the extent of my knowledge around collision prediction is, like the asteroid game. So instead, let me focus on this part here, which is on gaming. And I imagine multimodal AI creating, and generative AI, like just generative AI, being able to create amazing stories and gaming experiences for people. And it won't be long before this is here, and I can't wait for that. I think we need the prices of these things to come down a little bit. I also think there's a lot of concern around what the models will generate and ensuring that players get an experience which is at the proper rating, because it's hard to know what these things are going to generate for sure. Whereas when we have a fixed static game that is being shipped, it can be rated teen or it can be rated mature, and we can know that for sure. But when it's able to generate potentially anything it wants, even with really good guardrails, that's a concern. And I think that's prevented LLM driven games from coming to market so far. And I just want to talk raw for a minute here about my real thoughts on all of this stuff, this AI stuff, because my persona on YouTube, right, is that I'm really bullish on this stuff and I'm excited by this stuff. And it's true that I am. And I think people have many different aspects to their personality. Mostly everybody, right, has many different almost faces or something. What I'm trying to say is, I spent years learning these skills of programming, and I did it like most people learn the skills that they've learned. We do it the hard way, like through work and sacrifice, not being outside, being in front of a computer, spending hours debugging certain problems, not understanding things like on Stack Overflow, just digging for answers and figuring stuff out, and gradually getting there, right? And then a transformational technology like this comes around and kind of just levels all of that technical ability that you had. And this is hitting everybody. And it's kind of up to us now to, I think, adopt these new technologies in whatever capacity we can and focus our efforts on still doing what we love, but it just might be in a little bit of a different way. And that's okay. I'm just going to keep riffing on this. Okay. Honestly, go to the next video if you want, but I'm just... I'm going to share some more thoughts. So I think people are really capable of changing and still being very happy. I drank alcohol for whatever. I just drank, but I was getting kind of too into it. I was drinking every night a little bit, a third a bottle of wine type deal. And I wouldn't really be happy at night unless I had a drink. And it would kind of make me feel a little bit I just would feel like I'm not doing my night how I want to. And it would, and so I experienced this, I'm kind of an extreme person and I'm very prone to addiction in that sense. But I gave up alcohol, and now I don't think about it at all. I'm just as happy. I'd say I'm more happy because I'm happier about my health and I have less side effects like waking up groggy and stuff like that. But it's hard to say because, of course, I did enjoy drinking and it's a fun social activity. But either way, the point is I'm living a different life now. I'm still very satisfied in this life. And it's the same with my work. I'm not programming as much. I'm not getting my hands on the keyboard and writing the code as much. But I'm still very satisfied with my work for different reasons. It's allowed me to work a lot faster. My production and my output is a lot higher. And I can think more higher level. So it's almost analogous to going from an implementation person, a contributor in a company, to go into a manager level where you're now looking over contributors, and what you're outputting, your output is the sum of the contributors' work. And now you as an AI engineer, your output is the sum of your efforts into managing coding agents to some extent, right? I think I'm done. This final video of the course is about career development in AI engineering. And if you've got this far, first of all, congrats on getting through everything up to this point. This lesson is going to be very opinionated. This is my own belief about career development and working in AI engineering. And I want to be clear right off the bat, it's not about getting a job as an AI engineer or being called an AI engineer. That's not the goal. For me as an educator and teaching, it helps me position myself, so that I guess I get some trust from people. However, it's more, for me, it's always been more about the quality of work and the type of work and enjoying the type of work. So if you're like a database administrator, but you get to apply some of these ideas, these AI engineering concepts, great, that's awesome. If you're a data scientist and you can use LLMs to do stuff, that's awesome. If you're a software engineer and you're doing a lot of stuff with Cloud Code and developing work in the terminal and that's what you like, cool, that's great. It doesn't matter what you're called, right? It's the quality of work that we get to do. And so no matter what you're doing, I think it's really important, this concept of Kaizen. And I'll apply this to being a technical professional, how to apply this idea of Kaizen, which is this Japanese philosophy around continual growth, continual development, and the mentality around that. The last two categories on here, open source work and conference talks, these are really good for getting involved with other people, because I think it's like in the when we interact with other people is when the magic starts happening. Too much time alone and not interacting with the world is a problem. And these things, I will say from my own experience, have largely isolated me and caused me to do a lot of work alone without interacting too much with other people. And I wish if I had have gone back and redone stuff, I would have done more of these things. I would have definitely tried a lot harder to get into conferences and speak at these things. This is something I see myself investing in over the next 5 years of my life, trying to do a lot of stuff around conferences to, be meeting other people and getting out there. And open source contributions. Open source is something that, especially with AI tools, is just so approachable now. You can hop in and pick projects that you care about and attempt to make contributions to those things. And through the process, meet people and learn how software works. Speaking in public is an amazing way to boost your credibility. It's a great thing to include in your portfolio. It's a really strong indicator that you know what you're talking about and that you're confident, and people can see you too. If there is video recordings of these things, it lets people who are interested in working with you see what you're like and just kind of look at you and watch how you operate, and it increases networking opportunities significantly within that event. Like the people who saw you or the people you saw, you can just talk to them face to face. Hey, I'm a human. This is what I like. What do you like? And these soft skills and these interpersonal relationships, which become really, really important when it comes to jobs. I recently was on the committee of JupyterCon 2025. So I saw a lot of different topics, and I looked at hundreds. I think it was, I can't say the exact number, but it's in the order of hundreds of talks, submissions that were for talk proposals. So given what I saw and how we graded them and how we picked the ones that were going to make it to the conference, I've got a little bit of an idea of what might make a successful pitch for a conference. I think keeping it new and interesting right now and fitting within the theme of the conference. And ideally also you're picking something that you're really thinking about all the time, something that you work on this day to day. For example, it's an open source project of yours that you work on very consistently, or it's a very particular niche of this field that you're dedicated to, and this is your expertise. That's a strong signal that okay, this speaker is coming to talk about their stuff. And if all of these things are right and the stars align, then you'll get accepted to speak at the conference, and that would be very exciting. For what it's worth, here's what I've learned from many failed interviews, also my experience on the other side of the job as being the interviewer. First of all, you have to be all in on the job. They want to hear that you are talking to them because you want to work with them. That's all you want. This is your dream job. This is what you want to do. The next piece of advice is to signal your confidence that you can do the job. Whoever's interviewing you has a problem. At the end of the day, they need to fill some spot. Maybe someone's left and they're looking to replace that person. Maybe there's a new opportunity that's been created and they need someone to come in and there's a new business, or who knows what's going on. But they're looking for someone who fits a very particular persona. And this person they're looking for can do something. And you need to signal to them that you are that person, that you can do this. And even if you're unsure about yourself, they can't be unsure about you. They have to be positive that you're able to do this thing. The final idea I want to leave you with is Kaizen, which is this philosophy of continuous improvement. And lastly, the importance of staying curious. And when I say this, for me, the way this manifests is I encounter something I don't understand in my daily work. And even though it would be faster just to push the solution and continue on with my day, doing other stuff, maybe being productive, maybe logging off and doing something else off the computer, spending a bit of extra time to indulge your curiosity, right? Like, why is that? Those things pay off huge in the long run. So like, why is it that I install an MCP server using UVX as opposed to just copying that command and pasting it in? You think, what is UVX? Oh, okay, it comes from UV. Okay, but what UV is different than UVX. How does that work? And this sort of situation will play out constantly, all day long. And there's certain times you won't have the privilege of indulging your curiosity because you'll have to be pulled into work tasks or you'll be on tight deadlines. But when you have the opportunity, as much as possible, I would explore those things that you're naturally curious about in your work and deepen your knowledge of those concepts, because in the long run, that's how you'll be successful. All of these things will compound on each other. And one day we wake up and we're like, I can do all this stuff that I couldn't do before. And that's from all these small little acts of learning, no matter how small. And to really wrap this concept up, I have this note which I keep on my shelf, and hopefully you can see that. So it's from this Greek guy, Hesiod, and he says, if you add a little to a little and do that again, soon it shall be much. And I truly believe that. That's the end of my highlight pack for the AI Engineer Roadmap. And I'm really happy to be able to deliver this in a video form on YouTube for free, because this course means a lot to me. So I started building this in fall of 2024, and I spent many months working on the articles for this course. This was the core value proposition for most of 2025, where people were purchasing this course so that they could read these articles and see the code snippets and the figures, and they can also sign up, which you can do for free, and then just start tracking your progress by sort of ticking off and tracking your progress towards completion. But the real reason this course is so special to me is because of the content. So if you'll indulge me, I want to tell you about my history in my career. And before that, so I started studying physics. That's kind of where I think about my modern life beginning, is studying physics in graduate school. And I learned about statistics and I learned about mathematics, of course. And then after that, I had to work, make some money. So I became a data analyst, and I started using Python a lot and Jupyter Notebooks. And I published a book on Jupyter Notebooks and data science. And all the while I was having trouble getting data, like accessing it, cleaning it, storing it, making sure it was delivered daily. And so where I'm going with this is I started doing data engineering, and then I started getting called a data engineer. That was my job. And I did a lot of stuff with Redshift and SQL and data pipelines and orchestration and BigQuery over the years. And then most recently with these LLMs, I got really interested in this stuff and building with these things. And now I'm called an AI engineer. That's my job title. And so what I'm describing here, right, is my whole path has been kind of building all of the foundational skills, which I packed into this course and I'm teaching. For this reason, I've put an extremely large amount of time into this, but this just felt really special to me to be able to create this and provide this for you. And that's why I wanted to make it into a video course. And that's what I've done. So this was just the highlights of it. I've got the full video course learning experience complete over on zazencodes.com. And it feels amazing to have this as a completed piece of work. So at this point in the video, whether or not you're interested in purchasing this doesn't really matter. Thanks so much for getting this far and listening to me talk about my journey and being involved in my channel and what I'm doing here on YouTube. Namaste.